today we're going to add a little bit more to what we know about vectors. We know that a vector gives us a representation of a magnitude and a direction. So in our first example here, we have an angle of 115 degrees with a magnitude of 6. And what I want us to do is put this in component form. So remember, component form for a vector is V, and we want to make this look like a bold V, so let's try to make that a bold V. V is equal to, and this shows it's a vector, A and B. So how would we do it here if we had an angle of rotation of 115 degrees and a magnitude of 6? Now, some of you might be wondering why I'm going 115 degrees this direction. Does anybody see anything to do with bearings or headings? This does not have to do with bearings or headings. So we're back to what we need to think about as angles of rotation, this being the x-axis representing our initial side. Now, if we do, and we will at the end, do some word problems that deal with bearings, we'll be back with respect to north. But unless it says bearings or headings, what we're starting from is the initial side being the positive side of the x-axis with a rotation of, in this case, 115 degrees and a magnitude of 6. So how can we represent how to get from this point, which if we thought of it on the coordinate plane as the origin, to here, which gives us the component form for our vector that would describe the length and direction of the vector. So what we need is think about this just like we did when we were in that trig unit and draw down an altitude. From the altitude, we know that this represents our x and this length would represent our y, which in our form is the A and the B. So this is our x and this is our y. So if we're trying to find the x, if this is 115 degrees and we're working with this triangle here, we need to determine the angle measure here. So it's the 180 minus the 115. So this would give us an angle measure of 65 degrees. So there's our angle. Now, to find x, we should note that x is the adjacent side of this triangle when looking at the 65 degrees, y is the opposite, and the 6 is the hypotenuse. So we can find x simply by doing cosine of 65 is equal to x over the hypotenuse of 6. And we can find our y by doing sine of 65 because y is the opposite side. Now, to solve both of these, we'll just multiply by 6. So we multiply this side by 6 and this side by 6. So we get that x is approximately 2.54. And we do the same thing here. We'll multiply both sides by 6. And we get y is approximately 5.54. But when we look back, this is in the second quadrant. In the second quadrant, our x values are all negative. So when we're describing this vector in component form, we will show that it's a vector. This would be a negative 2.54, and this is positive 5.44. And that is the description of that vector in component form. If you notice, right here we multiplied by the magnitude times the cosine of the angle. The magnitude times the sine of the angle. So magnitude times the cosine gave us our x, and magnitude times the sine gave us our y. Let's see what happens on the next problem. Okay, problem number 2. Vector v has a length of 8 and a direction of pi over 3. So I've already sketched the picture for us here. So we have this angle of pi over 3, and that should be familiar to us because it is on the unit circle. So to find x, it's cosine of the angle equals x over 8. To find the y, this is going to be our opposite side. So we're going to do sine, and this should be y over 8. Okay, so for the first one, we're going to multiply both sides by 8, so we end up with 8 times the cosine of pi over 3 is equal to x. Now, we should remember from unit circle to the x value at pi over 3. Hopefully remember this. May not remember it at pi over 3, but hopefully 60 rings a bell. This is 1/2 comma square root of 3 over 2. So the cosine there would be our x value. So this is 8 times 1/2. So x is 4 for this vector. So for sine, we'd multiply both sides by 8. It would cancel on the one side, so we're left with that on the other. And we should be able to tell our y value is square root of 3 over 2. So this gives us 4 root 3 as our y value. So in vector form, in component form, this vector is represented by 4 comma 4 root 3. There is another form, and your book does use this, so I wanted to draw your attention to it. It's AI plus BJ form, where I is just representing that horizontal move and J is representing the vertical move. So this answer translated into that form would just be 4I plus 4 root 3J, and that's how that would look. These two mean the same thing. You are welcome to leave your answers in this form. And when the book asks for it to be in the AI plus BJ form, you're welcome to leave it in the component form there as well. Now, when we think of magnitude, we can use the absolute value bars to denote magnitude. So if we're talking about the magnitude of vector u, it would look like this. If we were talking about the magnitude of vector v, it would look like this. That's the magnitude. So if we look at the component form, did you notice each time to get our x value, it was the magnitude times the cosine of that angle? Let's go back and look at the last one. The magnitude of this one was 6 times the cosine of the angle. So our horizontal move can be represented by the magnitude times the cosine of the angle, and our vertical move is the magnitude times the sine. And so every time we write it in component form, this is what we end up having. Now, you're welcome to always draw the triangles and do it that way, but this is a shortcut. All right, given the vector, find the magnitude and direction. So here I have already drawn for us the vector. So if we go ahead and turn this into our right triangle, we've got a horizontal move of 3, a vertical move of 2 to represent this one. So does that not look like a right triangle? So to find the magnitude of vector u is just the Pythagorean theorem. It's the square root of a squared plus b squared. So the magnitude of u is the square root of 3 squared plus 2 squared. 9 plus 4 is 13. So the magnitude of this vector u, and the u should be bold, is the square root of 13. And there we go. Magnitude, the square root of a squared plus b squared. Now, to find the direction, if we look at this, we're trying to find this angle. So we were given the opposite, we were given the adjacent. So we're going to use tangent to find the angle measure. Tangent of theta equals the opposite side over the adjacent side. We'll have to use inverse tan to solve this now. And for this one, we're going to get an angle measure of 33.7 approximately. 33.7 degrees. So now we have our magnitude and our direction. All right, next problem. Here, we're in a different quadrant. We're in -2, -5. The magnitude is found the same way. So we're going to do the square root of -2 squared plus -5 squared. So the magnitude of the vector v is the square root of 29. Now the angle, if we look at this, what we're finding the angle of is this green arc here. And the angle of rotation is the red all the way around. So we're going to have to do a little work once we find this green angle. All right, so tangent of that angle, tangent of theta, the opposite side is -5. The adjacent side is -2. The tangent of that angle is approximately 68.2 degrees. All right, but we don't want this part. We want all the way around. So we have to add back in this part here, which is 180 degrees. So our angle of rotation here is 248.2 degrees. There's our direction. There's our magnitude. So you have to look at the quadrant that it's in and decide if it's in quadrant 2, we would have to subtract it from 180. If it's in quadrant 3, we would have to subtract it from 360. All right, so here we go. Vector u is represented by negative root 3 comma 1. Or if it was in ai plus bj form, it would be negative square root of 3i plus j. So the magnitude is going to be the square root of negative root 3 squared plus 1 squared. That's 3 plus 1 is 4. The square root of 4 is 2. For the direction, we should know this one. Hopefully we do. When we set this up, tangent of theta is equal to opposite over adjacent. We know in quadrant 2, when the tangent is negative 1 over the square root of 3, that is 5 pi over 6. Or 150 degrees. All right. Now let's take a look at the word problems. If you were not here yesterday, you can find this worksheet in the makeup folder that's located in the bins. All right, number 1, a jet is flying on a bearing of 65 degrees at 500 miles per hour. Find the component form of the velocity of the airplane. So if we take a look at this, how would this look? A bearing of 65 degrees. So now we're back to bearings. So since I'm back to bearings, I'm going back to north to orient my angle from. So it's 65 degrees and it's 500 miles per hour. Okay, so we're going to drop down that perpendicular. If this is 65, that leaves 25 here. So to find the component form, we could use our shortcut, or we could look at our triangle. This is our x, this is our y. So cosine of 25 is equal to x over 500. Sine of 25 is equal to y over 500. And we solve these. If you used your shortcut, you're punching straight in, which is what our next step would have been. 500 times cosine of 25 is our x. And 500 times sine of 25 gives us our y. So in vector form, component form of a vector, this would give us 453.15, comma, 211.31. The next problem. The pilot of an aircraft is faced with a wind speed of 40 miles per hour with a direction of degrees south of east. If the pilot sets a bearing of 20 degrees with a speed of 250 miles per hour, what is the actual speed of the aircraft? So we've got an aircraft that's facing some wind. Let's undo that and see if I can draw. Nope, can't even draw it this way. Last try. There's our north. Okay, so we have an aircraft that is facing the wind. Let's go ahead and represent the aircraft here. We've got a bearing of 20 degrees. So we want this to be about 20 degrees. So we'll say this is 20. Okay, and this is 250 miles per hour. Okay, now the wind is affecting this. The wind is, they are facing the wind, and we have a 40 degree bearing here. 40 degree south of east. So I went 40 degrees south of east, and the speed here of the wind is 40 miles per hour. So this is going to represent the plane, and this vector represents the wind. Now, what it's asking for is the actual speed of the aircraft. Well, the actual speed of the aircraft is the speed of the aircraft, but then we have to account for the wind. And one way we can do that is think of this. Let me go in here and copy this. And then we'll go ahead and paste that. And we'll think of this as being there. So that's what we need to think of this. And I'm going to change the color here on both of these so everything's not the same color. So do you see that these are equivalent vectors? They're the same length and they are parallel. So I can use it here with respect to the x-axis to find the effect here. And basically it's the sum of these two vectors. So we're going to find the plane and then the wind. And to get the result, we're going to add those two. So what we're looking for in the end is that vector. What does the result of the plane with the wind have? And that will give us the speed of the aircraft and the directional heading, because the direction is affected by that wind also. So for the plane, what we're going to do for the plane, I'm going to move these out of the way just for a moment so we can look at just what we need right now.
Zach Owen, if you're in Whitman, please come to the front office. Zach Owen, please come to the front
So
office.
here we go. We're going to drop it down, and you should see that it's going to be the 250 times the cosine of, well, if this is 20, what's this angle inside here? 70. And then the 250 times the sine of 70. So that gives us a vector. I didn't move these out of the way real well. We'll move them right down here for a second. Okay, so that gives us a vector here of 85.51, comma, 234.92. Now the wind is this one here. So this is going to be the 40 times the cosine of 40 degrees. This is going to be 40 times the sine of 40 degrees. And this gives us the 30.64 and negative 25.71. Okay, now the result would be the sum of these. So let's go back and think about what's happening. Basically, I'm taking this green one and adding it to this one so that I can get the resultant, which is the blue one. So let's see if I can change colors like this. So our result is the blue, and our wind is the green. Didn't get it all. Try one more time. All right, last try. Undo. There we go. Okay, so the resultant would be the sum of those two, and we're going to add those up. And we get 116.15 and 209. I think that was 71 and 92. So this is going to be 21. Okay. Now, what we're going to do to get the speed is the magnitude of the result. So the speed is going to be the square root of the sum of those squared. So the speed, in this case, is 239.29 miles per hour. Now, the angle is going to be tangent of theta. And what we're looking at is this blue here. We know the x, we know the y. So tangent is the y's over the x's. Opposite over adjacent. So that's 209.21 over the 116.15. And that gives us an angle measure of 60.96 degrees. Now let's think about where that is. That 60.96 is this angle. So how could we describe this? Okay, one way we could describe it is we could say it is, with respect to east, it is 60.96 degrees north of east. That's one way. Or if we just wanted to write it in terms of bearings, with respect to just north, we would have to subtract that 60.96 from the 90. So we would get a bearing of 29.04 degrees. So you could give either answer there. And we will save number 3 till Wednesday. Thank you.